Welcome to your second lecture, Probability Theory for Artificial Intelligence. This is your Professor Atif Fareed Muhammad. As we advance, we will delve into more sophisticated topics in probability theory, including measured theoretic probability and stochastic processes. These advanced theories form the backbone of many artificial intelligence algorithms, particularly in areas such as machine learning and natural language processing. Measured theoretic probability provides a rigorous framework for dealing with uncertainty and randomness, which is fundamental in developing probabilistic models. Stochastic processes, which model systems that evolve randomly over time, are particularly useful in artificial intelligence for sequential data analysis and time series forecasting. Advanced probability in artificial intelligence, AI systems model uncertainty, such as predictions, natural language, sensor data. You can say I eat food, you can say I eat cake, you can say I eat peanuts. All the post context is changing when you say I eat, and the post context is up to you whether it's breakfast, lunch, or dinner. The real world data is equal to noise plus randomness plus temporal dynamics. Foundational for Bayesian machine learning, reinforcement machine learning, or reinforcement learning such as MDPs or POMDPs. We'll look into these in depth. Time series forecasting, RNNs, transformers, probabilistic graphical models. These are the probabilities utilization in artificial intelligence as the base to get started with. Limitations of elementary probability, the sample spaces, events, probability rules, random variables with densities, mass function, infinite sample spaces, such as continuous spaces in reinforcement learning, convergence of algorithms such as LLN, CLT in high dimensions. Stochastic processes require handling infinity of RVs or RVS. Let's look into this with one example each. Elementary probability, reliant on finite sample spaces and simple event definitions, faces severe limitations in complex artificial intelligence systems like robotics, where state spaces are continuous and high dimensional, making it impossible to define events or assign probabilities using basic counting rules, as seen when a robot must assess collision risk across infinite possible obstacles, shapes, and trajectories. This foundational inadequacy directly comprises reliability, as tasks like sensor fusion and simultaneous localization and mapping require integrating continuous probability distributions and coherent beliefs updating processes dependent on measured theory and stochastic calculus. Meaning, without this advanced framework, robots cannot rigorously quantify uncertainty or make statistical optimal decisions, rendering them fragile in the face of the real world randomness. You might have witnessed the latest Waymo blackout. When the blackout happened of the electricity, all the Waymos in California stopped. So they had to get them off the street. That was an unknown phenomena for the Waymo taxi in specific. A random variable is a foundational concept that serves as a measurable function translating outcomes from an abstract sample space into quantifiable numerical values, which is essential for AI systems to process and analyze probabilistic events, such as a robotic sensor converting the physical world's continuous state into discrete, actionable data points For decision-making algorithms, infinite sample spaces present a significant challenge to classical probability as they require a move beyond simple counting to a measure theoretic framework to properly assign probabilities to events, which is critical in artificial intelligence applications like reinforcement learning, where an agent's state and action spaces are often continuous and unbound. The convergence of algorithms is a central concern in machine learning, where theorems like the law of large numbers and the central limit theorem provide the theoretical assurance that estimators such as stochastic gradient descent will stabilize to an optimal solutions as they process more data, guaranteeing the reliability of trained models in high dimensional spaces. Stochastic processes model systems that evolve randomly over time, such as stock prices or sensor noise, and are indispensable in artificial intelligence for sequential data analysis, enabling techniques in time series forecasting, natural language processing, and robotic path planning, where predictions depend on understanding temporal dynamics and dependencies. Hope this has been helpful to understand some limitations of elementary probability that we are discussing in this lecture. Mere theoretic probability, let's look into this in a little bit more depth. That measure theory generalizes length area to probability, applies sigma algebras probability as a measure. We will utilize in this healthcare example to diversify our learning. Mere theoretic probability provides the essential rigorous framework for healthcare artificial intelligence. By formally defining probability spaces to handle the complex, high dimensional, and often continuous nature of medical data, such as modeling the exact time to a clinical event, where a sigma algebra specifies measurable outcomes and the probability measure allows to precise likelihood calculations via integration over densities. This formalism underpins the convergence guarantees for machine learning algorithms trained on electronic health records, using theorems like the dominated convergence theorem to ensure model training stabilizes to a generalizable solution. And it also serves as the foundation for stochastic processes that model dynamic systems like disease progression or epidemic spread, enabling the creation of predictive tools for patient monitoring and intervention planning that translate advanced theory into clinical decision support. So now let's look into expanding this understanding in terms of the use of sigma algebras and information. So what is a sigma algebra? Collection of subsets, closed under complement, countable union, represents information or observable events. Rolling a die, 1, 2, 3, 4, 5, 6. It, if only told even or odd, this becomes a null set, 1, 3, 5, 2, 4, 6, or the whole set. The coarser F means less information. Let's apply this thing in the healthcare domain. In the domain of healthcare, a sigma algebra formally defines the set of observable or measurable events within a patient's outcome space, establishing the granularity of information available, such as distinguishing between the coarse events, such as glucose level is between 70 to 100, and an immeasurably precise value. This structure is intrinsically linked to information, where a coarser sigma algebra, like that form It technically forms a form of a basic signs monitor. Its basic vital sign monitor provides less detail, while a finer one, integrating data from ventilators to EEGs, enables the definition of complex clinical events for nuanced intervention. This hierarchy is fundamental for artificial intelligence as a predictive model's capability is bounded by the sigma algebra of its input data. Understanding this allows for the design of systems that optimally reason under partially observability, like remote monitoring, and quantifies the inherent uncertainty when working with coarser clinical information. Now let's look into random variables as measurable functions with an example, and this time we will be utilizing the robotics example. How about we combine robotics and electric vehicles domain in synchronicity to understand this topic at hand? A random variable acts as a measurable function that maps complex probabilistic world states to concrete numerical values, such as transforming a real world driving scenario into a quantifiable distance to a car ahead, with measurability ensuring that events like distance between 5 and 6 feet have well defined probabilistic for coherent reasoning. This framework underpins sensor fusion, where noisy LiDAR and camera readings are modeled as random variables and combines to create a more accurate estimated distance with a redefined probability distribution. And it extends to decision making, where actions are chosen by optimizing the expected value or probability of derived random variables representing outcomes like collision, risk, or energy consumption. Ultimately, this modeling enables rigorous safety validation, permitting engineers to analyze the distributions of performance metrics like the 99th percentile of braking distance, because a robot can be an electronic vehicle, and formulate probabilistic safety standards, providing a mathematical pathway to certifiable safety in unpredictable environments. So that is where we use random variables as measurable functions. The convergence theorem comes handy. It has three main pillars: monotone convergence theorem, MCT, increasing sequences; dominated convergence theorem, DCT, bounded sequences; and Fatu's lemma gives inequalities for limits. So I would strongly suggest you to conduct a little bit of research to understand what convergence theorem is, to establish an understanding in the area of interest that you might have. That can be robotics, healthcare, supply chain management, route optimization in the trucking industry, or the transportation optimization of a city like Washington metro area, or New York Transit, or New Jersey Transit, even the BART or the Bay Area Transit. Stochastic process, the collection of X over certain time of RVs, index time, discrete continuous. Let's look into this in a little bit more depth. The examples in artificial intelligence are stock prices in the finance world, word sequences in the natural language processing world, robotic sensor readings over time in the robotics domain. However, let's jump into with an example of word sequences using natural language processing. These processes provide the foundational framework for modeling language as a sequential probabilistic phenomenon in natural language processing, where a text or speech stream is treated as a collection of random variables indexed by time, capturing the inherent randomness and dependencies between linguistic units. This is implemented in architectures from classical n-gram models, which form Markov chains over vocabulary, to modern neural models like transformers that generate text autoregressively by sampling each new word from a distribution conditioned on the prior sequence, powering applications from machine translation to conversational AI. Furthermore, these processes enable advanced analysis through models like latent direct allocation or LDA for topic evolution and time series methods for tracking narrative shifts, while reinforcement learning frames dialogue as a controlled Markov decision process (MDP), permitting NLP systems to achieve a dynamic, statistically grounded understanding and generation of a language. Since we are discussing MDP, let's jump into this in a little bit more depth. We all have heard of AlphaGo that utilizes the game states from Markov processes. The framework for Markov decision processes provides the formal mathematical structure for modeling sequential decision making under uncertainty in natural language processing, defining a world with states like dialogue, context, actions like choosing the next word, and a reward signal based on user satisfaction or task completion, thereby transforming language problems into concrete optimization goals to find a policy that maximizes cumulative expected reward. Reinforcement learning serves as the solution suite for these MDPs when the model is unknown, permitting an agent such as conversational bot to learn an optimal policy through trial and error by interacting with an environment and adjusting its linguistic actions based on sparse delayed feedback, which is especially powerful for tasks where output quality is difficult to optimize directly with supervised learning, like generating engaging dialogue. This integration has driven significant advancement in sophisticated NLP applications in dialogue systems. Reinforcement learning optimizes for long term engagement and efficient resolution. In text generation, it fine tunes pre trained models using evaluation metrics as reward signals through reinforcement learning from human feedback. And in semantic parsing or translation, it enables agents to explore vast output spaces when a single correct answer is unknown but a reward can be determined for adequate execution. This approach allows natural language processing systems to learn complex goal oriented behaviors that are difficult to pre program, pushing the boundaries of interactive language understanding and use. Now let's look into Brownian motion. The Brownian motion, also known as the Wiener process, is a fundamental continuous time stochastic process that models the random erratic motion of particles suspended in a fluid. But its mathematical framework extends far beyond physics to become a cornerstone in financial modeling and generative artificial intelligence. It is defined by the three key properties. It starts at zero, has independent and normally distributed increments, and its paths are continuous but nowhere differentiable, representing a perfect model of pure randomness with no predictable trend. In finance, it forms the basis of the geometric Brownian motion used in the Black-Scholes model to simulate stock price movements, while in modern artificial intelligence, particularly in diffusion models, for image generation, the forward noising process that gradually destroys data structure is mathematically analogous to a Brownian motion. And the AI's task is to learn the complex reverse time dynamics to synthesize new coherent images from the noise. ITO calculus for AI. This is by itself is a whole domain. The use case I mentioned here is diffusion models such as DAL-E, stable diffusion, use STEs to model data generation as reverse time fusion. So let's look into this in a little bit more depth. Stochastic calculus extends traditional calculus to functions of stochastic processes like Brownian motion, as we are discussing in this current scenario, providing tools like ITO's lemma to solve stochastic differential equations, SDEs, that model systems with deterministic trends and random noise, which is crucial for AI in domains like finance and robotics. A transformative real-life use case is in diffusion models for image generation like DAL-E, stable diffusion, are the few couple of examples, where the forward noising process is framed as an STE analogous to Brownian motion, and the AI learns the reverse time STE to synthesize images from noise with ITO calculus, ensuring the mathematical rigor of this reversal. Beyond generative artificial intelligence, it underpins financial artificial intelligence for modeling asset prices and calculating risk matrix in simulated trading environments, and aids in robotics for state estimation and optimal control under continuous disturbances, enabling artificial intelligence to reason and intervene effectively in unpredictable systems. The Gaussian process. The AI application is Bayesian optimization for hyperparameter tuning, and I suggest you to look at the use of Gaussian process surrogate model and conduct a little bit of research to understand in depth that how you can utilize the GP, which technically is multivariate normal, and that is a suggestion that I would give you in specific, because conducting research allows you to expand your horizons to understand what a process is in terms of GP, and then we'll go from there beyond. While I always urge you to conduct research to establish your understanding on top of what we are discussing in this lecture, I assure you that Gaussian processes are a powerful non-parametric Bayesian framework used for regression and classification that, instead of predicting a single value, define a distribution over possible functions that fit the observed data, characterized entirely by a mean function and a kernel function that encodes assumptions about the function's smoothness and periodicity. In machine learning, GPs excel in scenarios with limited data and a need for uncertainty quantification, as they provide not just predictions but also a measure of confidence, the predictive variance for each estimate, making them invaluable for applications like Bayesian optimization, where they act as surrogate model to efficiently find the optimum expensive to evaluate functions such as hyperparameter tuning for neural networks or robotic controller parameters. Further, their flexibility and principled uncertainty estimates have led to their use in geostatistics, robotics, for spatial modeling, and even as components in deep learning, demonstrating their versatility as a robust tool for probabilistic inference in decision making under uncertainty. Now let's look into hidden Markov models. The uses for AI are speech recognition, bioinformatics, parts of speech tagging, and natural language processing. So we will consider our next few discussions will be on speech recognition. HMMs or hidden Markov models have long been a foundational tool for automatic speech recognition by modeling spoken audio as an observable sequence of acoustic features generated by an underlying hidden process of phonetic states, where each state has transition probabilities to other states and an emission probability distribution over possible acoustic observations. Recognition involves using a White-Tree algorithm to find the most probable sequence of hidden states given the audio input, which is then translated into words using a language model for linguistic coherence, while training is achieved using Baum-Welch algorithm that iteratively adjusts transition and emission probabilities from transcribed speech data. Despite the rise of deep learning, HMM principles persist in modern hybrid systems where deep neural networks replace traditional emission models to better estimate state probabilities, with the HMM framework providing the essential temporal modeling to use these states into coherent words, demonstrating its enduring value for handling the sequential uncertainty of spoken language. Why should we care? We will look into handling uncertainty, making predictions, learning from data, decision making under risk, model complex systems, robustness, and generation. So this is very important that we take care of all these aspects when we are dealing with the use of statistics in the arena of artificial intelligence, data science, or machine learning. Handling uncertainty, AI systems often operate in environments where information is incomplete or noisy. Probability provides a framework to quantify and manage uncertainty, permitting artificial intelligence to make reasonable decisions even when outcomes are not certain. So if you are dealing with the healthcare and you need specialization, you have to go these 4 different routes. If your standard PCP or primary care provider refers you to a specialist, that can refer you to the next level of specialization needs within the healthcare domain. So you can look at immunotherapy, radiation therapy, chemotherapy, and surgery. These are few of the areas where handling uncertainty is taken care. Making predictions, many AI tasks such as classification, regression, and forecasting rely on predicting future events or outcomes like stock prices, the possible snowstorm, or a tornado. Probability models like Bayesian networks or Markov models enable artificial intelligence to assign likelihoods to different possibilities, making predictions more robust and interpretable. Learning from data. Machine learning, a subset of artificial intelligence, is fundamentally about learning patterns from data. Probabilistic models such as Gaussian processes, hidden Markov models help in understanding data distributions, estimating parameters, and updating beliefs as new data arrives. Decision making under risk. AI systems often need to make decisions with associated risks. Probability theory, especially Bayesian decision theory, helps in evaluating the expected outcomes of different actions and choosing the optimal one. Modeling complex systems, robotics, electronic vehicles like Tesla or Waymo, all these are complex real world systems. Other than natural language processing, financial markets predictions, or biological processes are inherently probabilistic. AI uses probabilistic graphical models to represent and reason about these complex interconnected systems. Robustness and generalization. The probabilistic approach help AI models generalize better to unseen data by accounting for variability and noise rather than relying on rigid deterministic results. In this lecture, we have discussed measure theory that provides rigorous probability foundations, stochastic processes, model randomness over time, key for sequential AI tasks, Markov, Gaussian, Poisson process. Even though the Poisson process has not been discussed in this lecture in depth, but I strongly suggest you to look into this and conduct research using Google Scholar or IEEE Explore. Each model different AI relevant phenomena. Each model can actually improve different phenomena. And since now we are dealing with AI almost in every arena that works. Python implementation allows us to bridge theory to practice. SciPy, TensorFlow are some tools that you can look into to perform these tasks. Now you can formalize uncertainty in AI models, implement and simulate complex stochastic dynamics, read advanced reinforcement learning generative AI papers with probability foundations. Happy learning. See you in the next lecture.